Gauss's law is a little different, though, in that although Coulomb's law is a true representation of the electric field force between two charged particles, Gauss's law is a different kind of explanation. First, Gauss's law represents the first of the four Maxwell's equations. Maxwell's equations are a group of four equations that can successfully predict and determine almost all of electronic behavior. So they're kind of fascinating, and Gauss's law is the first one. Now, we're going to see a modified version of Gauss's law that we will slowly build on over the course of the year, so that by the end we'll have the complete version of Gauss's law. But Gauss's law is a little bit bizarre, and it takes a little getting used to. It's got a lot of parts to it, and because of that, it can be, in some cases, overwhelming to students. So, as opposed to doing anything with it today, I want to just talk about the structure of Gauss's law and what it intends to tell you. First, we're going to have to learn about some new words here. First, this portion of the law is known as electric flux. Flux calculations are calculations that attempt to find out how much of a field passes through an area. There are lots of different flux calculations out there, but with the term flux, which is derived from a word meaning to flow, indicates the amount of electric field that passes through an area. So when we talk about calculating flux, in the case of this problem, we're talking about how much electric field passes through an area. Now, when we talk about passing through an area, we're talking a physical area. Like, how many of you have ever skimmed a pool before? Like skimmed the stuff off the top of a pool? Or can imagine it being done, right? You've got the net on the end of a little pole there. Imagine the net is the area. Like there's an area to that net, because there is, right? A length and a width. And if you pass it through the water that passes through that net would be considered the water flux as it goes through the net. So the deeper you dip that net into the water, the more water flux would be passing through the net. Does that make sense? If you only had a little tiny corner in there, you wouldn't have very much water flux passing through the net. So all flux is a sum of how much of something is flowing through an area. There's going to be more to it than that, because electric fields have direction. What you don't know yet, what you're going to have to learn, is that area has direction too. It's not just about how much electric field passes through the area, it's also represented based on what angle the electric field presents to the area. We'll talk about that a little bit too tomorrow. And that's why there's the dot here. That dot isn't multiplication, that dot is the dot product. It's a scalar product that produces a scalar from two vectors. And it tells you how much of the electric field is in the direction of the area. That's what it means. Now, lots of symbology here, but clearly we've got a summation symbol, but it's a summation symbol with a circle drawn through it. This is important and probably bears a little bit of a deeper explanation. In order for you can calculate any flux, but to qualify as Gauss's law, the flux has to be in a closed and bound surface, meaning our surface has to be a three-dimensionally closed surface, like a ball or a box, something that is completely bounded. So a sheet of paper wouldn't qualify as a closed and bounded surface, but a box would, a cylinder top and bottom, that would be a closed and bounded surface. You just have to account for all of the area. So our summation might break up into the amount of flux through each of the sides of a cube, or the amount of flux that passes through the sides, top, and bottom of a can. Or we could use a sphere. Either way, This summation requires that you add up all the flux passing through a closed and bounded surface. That's what all that stuff is. In fact, there's a symbol used for flux. It's like an I with a circle in the middle of it. Put a little E there to say electric flux. And you could write flux using this symbol instead. If you do that, then Gauss's law would look even simpler. Now, Gauss's law is a proportionality. It says the amount of flux passing through a surface is proportional to how much charge is enclosed inside that surface. That's what this says. Again, if you add up all of the electric flux passing through a surface, it's proportional to how much charge is inside that surface. So imagine you put a candle inside a ball, a clear ball. You would be adding up all the light that passed through the ball, and it would tell you how much light is being given off from the candle by adding up all the light that passes through the surface of that ball. It's similar here. We're saying that if you could add up all of the electric field that goes through the area, it would tell you how much charge is inside that area. This is a new symbol for you, and it's lowercase epsilon. And we'll say the words epsilon naught a lot. It's called the permittivity constant. We're going to pick this up tomorrow right here, but I'm going to encourage you to come tomorrow with an open mind and be ready, all right? So let's say this is the electric field, and we're dealing with a relatively uniform electric field. And I have a skimmer, a rectangle. I'm going to take my rectangle and put it in there to try and skim some of the lines. You see how I've kind of lassoed some of those lines? I've tried to line up the electric field, the skimmer in such a way that it is perfectly aligned with the direction of the electric field. This area would have a direction that would be perpendicular to the surface. So right now, the electric field and the area are in the same direction. The dot ends up being a product between a piece of area and the electric field, and then we determine how much of the electric field is in the direction of the area by using the cosine. The way I have it arranged now, I've made it as aligned as possible, and the direction would be 0 degrees. This would be the angle for theta that I would use to describe the direction of the electric field versus the direction of the area. Is that all good so far? Does it make some reasonable sense? This is a good time to ask if you don't understand. Because I think you can imagine that if I start to turn it, and from now on I'm not going to draw I'm not even going to try for 3D. If this was the direction of the skimmer in the electric field, and I decide to turn it just as a little bit, well, now the direction of the area makes an angle with respect to the electric field. You can imagine I could continually tip this area until, not like that. Till the area was this way and I was perpendicular to the field. Would any field lines pass through this particular arrangement? So the thing I want to point out as we do this is that one of the things we're going to attempt to do is try to minimize our dependence on the area by choosing shapes and such that allow us to control what the angle is for the flux. And I know it doesn't make a whole lot of sense right now, but there are ways to do that. And one of them has to do with paying particular attention to the type of shape I'm going to use and the purpose of using a shape at all. Let me advance this just a little bit, but right now, do we understand what I mean when I say that area has direction? All right. Let me erase all this for a minute. Imagine some random shape, but now I'm dealing with a closed, bounded shape. If I pick any point on the shape, I can get an idea for what the direction of the area is by imagining a tangent line at that point and drawing an arrow perpendicular to that tangent line. Do you guys all see what I'm doing? Just picking random locations. Each one of these represents a bit of an area along some closed and bound surface. Now, in this example, you'll notice that anything that's on the left side of this has an area that's generally pointing to the left, but an electric field that's going to the right. Do you guys see that? No matter which one of these points I choose, let's choose this one right here. The electric field is this way, but my bit of area is clearly to the left. Similarly right here, the electric field is this way, but the bit of area is generally to the left. In fact, no matter which one of these I choose, do you notice that I'm going to get an angle greater than 90 degrees? No matter which one of those surfaces I choose, anywhere on that left side. So on the left side of the green line. On the other hand, on the right side of the green line, my angles are all going to be less than 90 degrees. Well, maybe not that one right there. Maybe my green line isn't great. But that suggests that on this side, cosine is going to be negative, and on this side, cosine is going to be positive, right? Because cosine for any angle that is less than 90 degrees is positive. Positive first and fourth quadrant. And anything greater than 90 degrees is negative. Y'all follow along okay? This all making sense. You see, this shape that I've drawn has a flux of 0. As many of these electric field lines that enter the shape, I have the same number of field lines that exit the shape. But there's a lot of reasons I know that the flux has to be 0. One of them is because of this simple argument I'm making about the field lines all entering and exiting my shape. But the second one goes back to a central tenet of Gauss's law. If I add up all of these electric field contributions, I'll notice that ultimately, based on Gauss's law, there will only be a net flux if I've enclosed charged particles. Enclosing electric field isn't enough. I have to enclose charged particles. Fields can pass into and out of your area. That's fine. But the Gauss's law indicates that you will have a net electric flux, meaning more positive or more negative, if you enclose a charged particle. Now, Hans, okay. I'm trying to be super careful and super deliberate here. Gauss's law indicates that there will be a net flux, meaning you will have more lines exiting than entering if you enclose a charge, or more lines entering than exiting. Consider something like this. We have an idea for what the electric field looks like around a single point charge. We've kind of talked about it a little bit, but we know that the electric fields originate from a single point charge. Gauss's law states that if I enclose a space somewhere, anywhere in the universe, that the amount of charge I enclose will be equal to or proportional to the net flux. I can use the word net here because a summation is still a sum, and the word net means sum. Now, based on the surface I've chosen, I think it's pretty clear that I've enclosed no charge. I will have a flux of 0. As much electric field will enter this region as exit this region. Does that make sense? You guys following that so far? But if I choose this surface is going to have a flux that's going to be proportional to the Q enclosed, in this case, capital Q, because I have enclosed this charge. In fact, if this is surface A and this is surface B, the flux for surface B is 0. But the flux for surface A is Q over a proportionality constant. I don't know anything about the electric field or the area to be able to determine that, since I was given the value of the charge. Gauss's law tells me a way to figure out how much flux there is. Now, don't get me wrong. I don't know if knowing how much flux there is going to matter or not, or if it's going to have any impact. All I do know is that Gauss's law, being a law, allows you to make that specific generalization. In fact, one of the problems that you'll be faced with, usually on multiple choice, is you'll have a collection of charges in space. Can you draw a shape that would enclose charges but have no flux? I could. I see a couple ways to do so. Do you? I mean, I could go would that do it? I don't think so. I've enclosed charges, and the net charge enclosed is 10Q. That probably won't do it. What's the total charge enclosed now? Yeah, it's not going to do it, is it? Do you see one that could enclose charges but would have a net flux of 0? right? Wouldn't that do it? The flux through this surface would have to be 0. Now, I'm bringing this up on purpose because what you have to understand is there's clearly a complicated electric field in this region, isn't there? There are electric field lines going every which way. I have no idea what this electric field would even look like. But that's not what flux is about. Flux is a combination of not just the amount of electric field, but what direction it passes through a surface. So the law isn't about whether there is or is not an electric field in this region of space. The law states that the number of field lines going in will equal the number of field lines going out for this surface. Why? Because the net enclosed charge is 0. This is what Gauss's law is about. Now, I'm going to be very clear about this. The usefulness of Gauss's law might be in question here. How useful can it be? You're drawing shapes to which I could never really figure out their geometry. And more importantly, what's the point if all you're going to do is tell me, okay, great, so this surface, surface A, has a flux of 0. Well, Gauss's law has more use than this. This kind of an ancillary idea that you could find surfaces that would enclose charges that are equivalent to 0. Yes, it's true that that would mean that the flux in that through that surface is 0. Gauss's law can be used in another way, a way that might have a little more power. But it involves recognizing symmetry and understanding the nature of this dot product. Let me give you an example of a way that we could use Gauss's law in perhaps a more functional way by being very careful about choices we make. Consider a single point charge, Q, in space. I know something about the symmetry here because we've been talking about it. I know the electric field for this point charge is going to decay as I get further away, but I know that it's got to be spherically symmetrical. So I'm going to see if I can use Gauss's law to tell me something about the electric field around this point charge. First, I want to choose a surface that exploits the symmetry of this arrangement. So I'm thinking a square probably won't exploit any symmetry because every point on the square is a different distance away and probably doesn't give me the kind of symmetry. Like, I don't know what this angle will be between the electric field and the area of the box any better than I know what this angle might be between the box and the electric field. However, I could probably choose a sphere. And if I'm careful, make the sphere concentric with the charge. Does that word concentric mean something to you? It means they share the same center. Now, if I'm doing this carefully, every ray of the electric field, this one say, it's going to be perfectly aligned with the piece of the area that it passes through. Do you guys see that? For every single one of these, the rays have to exit the surface of the field at an angle of 0 degrees relative to the surface. You guys are seeing this, right? You understand why I'm saying every one of these is going to have a theta equal to 0 degrees. This is the angle between the electric field and the bit of area. If I choose my surface correctly, maybe I could make it consistent like this. Moreover, that would suggest something else too, that if I start by looking at the flux, I could immediately write this in terms of a product. where every single theta would be 0 degrees. I'm carefully choosing my situation. I'm choosing a surface, a Gaussian surface. I'm making it completely bounded, meaning I'm using a sphere to try and come up with an expression for the flux. Put my bars top and bottom as to not confuse anybody. Now, I'm also going to point out something else we know. We know that if we're equidistant away all the time, that the electric field should be the same size everywhere where it goes through that surface. Do you guys agree with that? That the strength of the electric field had to be the same everywhere as it exits the surface because I'm the same distance away from the charge everywhere? Well, in a summation, if the electric field doesn't have anything to do with the area, then I can pull the electric field outside of the summation. Now, if I add up all of the area of a sphere, I would just have the surface area of a sphere, right? So far, has this argument been okay? I know you're wondering, well, so? Gauss's law says Q enclosed equals epsilon naught times the flux. But I have an expression for the flux now. Sorry. Surface area of a sphere is not 4 pi r. No one corrected me, thank you. R squared. I'm going to keep going, okay? But we're almost at the end. You can use Gauss's law to come up with expressions for electric fields. And if you look closely at this one, you get something that looks an awful lot like Coulomb's law. Do you guys all see it? The only difference is that instead of K, I have this complicated guy. The truth is, one of the things Gauss's law can do, and what it's very good at doing, is finding the electric field for shapes that have for shapes that have very established symmetry. It can do very complicated problems for problems that have very established symmetry. You have to understand the symmetry to be able to use Gauss's law. But Gauss's law can be used to figure out the electric field in very interesting circumstances. To use Gauss's law, you have to understand, though, you are choosing a Gaussian surface. That's what this is called. Gaussian surface might as well serve the same role as a test charge. You're not actually creating a surface. You're creating something that you can integrate over. A three-dimensional object that can be used to exploit the symmetry of some kind of charged shape. And by using the symmetry of the situation, you can use a Gaussian surface to help give you an expression for an electric field. Now, I do want to handle this. This is K. Epsilon naught is known as the permittivity constant. The permittivity constant. And I do from the point charge is that it predicts Coulomb's law. There are basically three basic shapes you have to be able to do here. The point charge, the infinite line, and the infinite sheet. We've set these up using Gauss's law. Remember, we use the disk to act like the infinite sheet by talking about what is the electric field near a big disk of charge. Do you guys remember that? And we set up the line of charge but didn't solve it because the math was complicated. The integral was complicated. Let me ask you something. And I want you to think about this. In fact, I want you to draw up on your paper. Imagine I have a very long line of charge density lambda, infinitely long. So this is a view of it from the side, and this is a view of it head on. What do you think the electric field would look like around this line of charge?
Arrows going outward from
Draw a picture. You describing arrows going outward. I don't want to hear it. Draw a picture. If I were going to use a cylinder, probably wrap it in such a way as to try and exploit the symmetry here. You see why this would exploit the symmetry around this line? We're going to pick this up tomorrow here. Explain what it was yesterday, but today, let's explain it. The permittivity constant is we believe it's one of those constants that's the same everywhere in the universe. So there's only a few natural constants like this, but it's a natural constant, which means that its value depends on the units that you're using. It's analogous to G, the universal gravitational constant, which we did talk about last year. Its value, 6.67 times 10 to the negative 11th, is arbitrary. It's based on the fact that we are in newtons, meters, and kilograms. So the permittivity constant is similar. The permittivity constant tells you how well an electric field can be established in space. That's what it tells you. Permittivity constant tells you how well an electric field can be established in space. The naught means we're talking about the permittivity constant of a vacuum. 1C, 2 U's, right? Not 2 C's? Or is it 2 C's? Okay. Since I can't spell, you might also see it written free space. That's okay too. But the naught means the permittivity of free space. Now, you can manipulate permittivity. You can't manipulate gravity, but you can manipulate permittivity. There are materials out there called dielectrics that can increase the permittivity of free space and make the permittivity higher, meaning that for your same amount of charge, you get more electric field. So materials called dielectrics change the permittivity. They use lowercase kappa as something called the dielectric constant. And although we're not going to talk about it much for the time being, dielectric constants are just scalar values that scale the size of the permittivity. There are lots of different materials out there that increase. In fact, almost every single material in the universe has a higher permittivity than the permittivity of free space. Permittivity of free space is 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. And if you take 1 over 4 times 3.14 times 8.85 times 10 to the negative 12th, you'll get 9 times 10 to the 9th. You could do that as an exercise, but it's not that important. K is defined as 4 pi epsilon naught, not the reverse. Coulomb's constant is not a real constant. It's a constant based on an actual constant that can be measured separately, the permittivity of free space. Now, we are going to learn about 2 major constants in this class. One of them is the permittivity of free space. The other one is the permeability of free space. One is how well an electric field can be established in free space. The other one is how well a magnetic field can be established in free space. it might interest you to know that the two of these define how fast light can propagate in space. In fact, they can predict that light is an electromagnetic wave and predict its velocity. Because how fast an electric field and a magnetic field can be established in space determines how fast light will propagate. So there's some interesting things that connect these two these two constants together, but it's important to understand that they can be measured independently and then predict the existence of electromagnetic radiation. So there's some pretty powerful stuff here in the future, but right now we're just grasping at this idea of permittivity. How well can an electric field be established in free space? Now, we did the point charge, and what I want